Okay, I should mention now that I'm at this point that some ways of writing are, you can write it this way, set of all x, y, such that x is between a and b, and y is between c and d. And this is mentioned on page 2 in the notes. There is a typo regarding this part. Y is supposed to be between c and d. I had switched y and c. Thank you, Allegra, for finding that. So it's on page 2. Or another way of writing for rectangles is AB Cartesian product with C and D. So you can find a rectangle as a Cartesian product of two intervals, where it's understood that this refers to x and this refers to y, sort of by convention. But certainly this way is a little more clearer. That was redundant, a little more clearer. Okay. Oh. All right. Okay. What we'd like to be able to do, of course, is have a practical way of evaluating a double integral, just like we have for single integrals. And the way that you do that through a result called Boobies Theorem. States that double integral over a rectangle can be computed in either of two ways. If f is continuous, certainly you can do this. It's not absolutely required that it's continuous, but at least if it's continuous, this is sufficient on the rectangle. Okay. So one way you can evaluate it is as follows. You take f of xy and you integrate it from c to d with respect to y, where x is treated as a constant. So it's like partial differentiation, where you're differentiating with respect to one variable and you're holding the other variable fixed. You act as if it's a constant. And the result of this is now going to be a function of x, because this is a definite integral here. Once you plug in these limits, you're not going to see y anymore. So you get a function of x, which you now integrate from a to b dx. So this whole thing is called an iterated integral. So you can treat a double integral as two single integrals evaluated in sequence like that. So that's one way to do it. The other way to do it is take f of xy, integrate it from a to b with respect to x. So now y is treated as if it were a constant. The result of this whole thing is now a function of y, which you now integrate from c to d. So the order, so as long as you have this continuity of f on the rectangle, then the order doesn't matter. Okay. So, double integral as of a dA, but it's perfectly acceptable to write it this way as well, dx dy or dy dx. I think both books normally use this convention until it's time to actually start evaluating it, and then they switch to one of these forms and you fill in the limits of integration for the rectangle. So to give a preview of what we're going to talk about on Thursday, if a result of this inner integral is going to be a function of x anyway, there's no reason why c and d cannot be functions of x as well. And that opens the door to integrating over more complicated regions than just rectangles. So that's Thursday's topic. By the way, so for those of you who are attending the review session tonight, and especially for those of you who were not in my class last semester, I serve refreshments at these things. And at least the 8 students who showed up last night didn't gobble them all up. Okay. So, let's let R be this rectangle. So x goes from 0 to 1, y goes from 0 to 2, and our function is x squared y plus x y cubed. So now we're going to integrate this over rectangle using the Boobies theorem. So we'll do integrating along the y direction first, and then with respect to x. So we're going to have x squared y plus x y cubed dy, and then a result of that we'll integrate with respect to x. So certainly you can, just like before, you can treat each term separately, and this is where you have to remember to treat y as a constant. No. X, got us a differentiation nightmare all over again. We're treating x as a constant. So, what we can do is, if x is going to be a constant and we're integrating with respect to y, we can pull the x squared out. So now what we're going to have is x squared, integral from 0 to 2, y dy, and then for the other term, x we can pull out, x from 0 to 2, y cubed dy, dx. So now we can integrate these in the usual manner. So now we're going to have x squared, y squared over 2 evaluated at 0 and 2, and then x y to the 4th over 4 evaluated at 0 and 2. And we're going to plug in these limits just for y. So once we do that, we're going to leave x alone, and what we'll have is a function of x, and then we integrate that. Okay, so we plug in 0 and 2. When we plug in a 0, we're not going to get anything. So we're just going to get 2x squared. And over here, we're going to plug in 2 and get the 16 over. So 4x dx. So now we're down to a single integral. So 2x cubed over 3 plus 4x squared over 2. Evaluated at 0 and 1. So we get 8/3 for the result. So you pick either variable to integrate with respect to, hold the opposite variable, or all other variables fixed, treat them as constants, and go from there. So question. So 0 to 2 with respect to y is the outer integral. Now we have integral from 0 to 1 is x. X squared y plus x y cubed dx dy. So now what we do is we treat y as a constant and we're integrating with respect to x. So we're going to get y x cubed over 3 plus y cubed x squared over 2 evaluated at the limits 0 and 1. So we just plug in those limits, so we get